In the summer of 2020, a team of scientists from the University of Miami boarded the research vessel Ocean Explorer and set off into the Red Sea on what was supposed to be a routine mapping expedition, nothing more than a detailed survey of the seafloor's structure. Nobody aboard expected to find anything that would upend basic assumptions about what the deep ocean was even capable of hiding. As the ship reached its target coordinates, the crew lowered a deep sea submersible fitted with cameras and powerful lights over the side, watching it sink slowly through darkening water until it passed the 1-mile mark, a depth so far below the surface that not a single photon of sunlight has ever reached it. In that total, crushing blackness, the submersible's lights swept across what looked at first like an unremarkable stretch of empty seafloor. Then the picture on the monitors changed. Something flat, strange, and unmistakably geometric came into view. A smooth, glassy expanse roughly 70 feet across, with a thin, almost ghostly mist hovering just above its surface. For a moment, the researchers assumed they were looking at disturbed sand or a drifting layer of silt kicked up by a current. But as the submersible eased closer, the truth became impossible to dismiss. They weren't looking at sediment at all. They were looking at a lake, sitting on the bottom of the ocean, more than a mile beneath the waves, with its own sharply defined shoreline separating its water from the seawater surrounding it on every side. It sounds like something that shouldn't be able to exist. An entire self-contained body of water hiding inside another body of water. And yet, what the Miami team had stumbled onto turned out to be one of the strangest, most lethal, and most scientifically important phenomena anywhere on the planet. In the years since that Red Sea dive, researchers have identified more of these hidden lakes, studied their chemistry in painstaking detail, and confirmed something that sounds almost too extreme to believe. Their waters kill nearly anything that touches them, instantly and without mercy. And yet, somehow, inside that same lethal environment, scientists have found life. Organisms so radically different from anything else on Earth that they've forced a rethink of what it even means for a place to be habitable. How can something this deadly exist on our own planet's ocean floor? What natural process could possibly build it? Why does its water function like a chemical death trap for every fish, crab, and creature that swims into it? And how, against every apparent rule of biology, is something managing to live there anyway? Let's go all the way down and find out. Follow-up research quickly revealed that the Red Sea Lake wasn't a one-off oddity. Scientists have now cataloged roughly 25 similar formations, scattered across that same region alone, varying wildly in shape and size, but sharing the same essential nature. And remarkably, formations like this have only ever been documented in 3 places on the entire planet: the Red Sea, the Gulf of Mexico, and the Eastern Mediterranean, and nowhere else. Some of these underwater lakes are barely larger than a living room. Others are true giants. The Orca Basin, sitting in the depths of the Gulf of Mexico, sprawls across roughly 47.5 square miles and reaches a depth of around 720 feet. So vast that actual underwater waterfalls form within it, cascading over irregularities in the seafloor terrain beneath the surface of the lake itself. Whether tiny or immense, every one of these formations shares a single defining trait, and that trait is the first real clue to understanding how something this strange can exist at all: extreme salinity. Salt makes water denser and heavier than fresh water, something you can measure directly, since a liter of ordinary seawater weighs roughly 0.8 to 1 ounce more than the same volume of fresh water. But the water inside these underwater lakes takes that principle to an entirely different extreme. Their salinity runs somewhere between 8 and 10 times higher than normal seawater, dense enough that this heavy brine sinks and settles directly onto the seafloor, forming a distinct, separate layer rather than mixing with the ocean above it. Scientists refer to these formations by a fitting name: brine pools. Extreme salinity alone doesn't explain the full mystery, though. Where does all that salt actually come from, and how has it managed to persist on the seafloor, undissolved and unmixed, for what researchers now believe can be thousands or even millions of years in some cases? If physics were left entirely unchecked, that dense salty water should eventually rise, carrying its salt content upward until it fully blended into the surrounding sea. That process does happen, slowly, but it's continuously offset by a steady influx of new, warm, salt-rich water flowing in from below, keeping the whole system in a strange, ongoing equilibrium. Which raises the next obvious question: what exactly is feeding that source, warming the lake and continuously resupplying its salt at the same time? The answer traces back to the deep geological history of these 3 specific regions. At various points across Earth's history, the Gulf of Mexico, the Eastern Mediterranean, and the Red Sea were each completely cut off from the global ocean, sealed shut by the slow, grinding movement of tectonic plates as continents drifted, collided, and reshaped the planet's coastlines over tens of millions of years. Once isolated, each of these basins effectively became an enormous inland sea, and over enormous stretches of time, that trapped water simply evaporated away entirely, leaving behind massive deposits of pure salt where an ocean used to sit. Later, sediment slowly buried those ancient salt beds under new layers of rock. Eventually, renewed tectonic activity reopened a connection to the wider ocean, and seawater flowed back in, filling these basins once more. What that leaves behind today is a layered structure on the ocean floor, a cap of ordinary sedimentary rock, sitting directly on top of colossal buried slabs of ancient salt. The final ingredient needed to actually activate a brine pool is ongoing tectonic activity, which keeps cracking and fracturing the seafloor in these regions. Seawater seeps down through those fractures until it reaches the buried salt layer, dissolving it and turning into an intensely concentrated brine. Warmed by heat radiating up from deep within the Earth's crust, that dense, salty, superheated water rises back toward the surface, but because it remains so much denser than the ocean water around it, it settles right back down onto the seafloor instead of dispersing, continuously replenishing the lake from below. That's the entire mechanism. A self-sustaining, naturally occurring reservoir of extraordinarily salty water, constantly topped up with minerals and heat from deep inside the planet. In effect, these brine pools function like alien worlds sitting right here on Earth's own ocean floor, their chemistry, temperature, and pressure resembling conditions you'd expect to find on a distant exoplanet rather than anywhere on our own. To be absolutely clear on one point before going further, no, a person could never actually swim in a lake like this. Setting aside the chemistry entirely, the crushing pressure at a depth of over a mile would destroy a human body long before it ever reached the lake's surface. But it's worth running a thought experiment anyway, imagining what it would actually feel like if one of these lakes somehow existed on land instead of the ocean floor. The very first thing you'd notice stepping into it would be the density of the water itself, far thicker than anything you've ever experienced, closer to viscous syrup than liquid, resisting your movement at every step. You genuinely couldn't drown in it. The density is so extreme that it would physically push your body back up toward the surface, almost like standing on a liquid mirror. Next would come the smell, and by most accounts, it's among the worst odors imaginable, caused by hydrogen sulfide gas continuously released from the brine, producing an overpowering, concentrated stench of rotten eggs thick enough to hang in the air around the entire lake. As bad as that smell is, though, it's nothing compared to what happens the moment your skin actually makes contact with the water itself. At various points across Earth's history, the Gulf of Mexico, the Eastern Mediterranean, and the Red Sea were each completely cut off from the global ocean, sealed shut by the slow, grinding movement of tectonic plates as continents drifted, collided, and reshaped the planet's coastlines over tens of millions of years. Once isolated, each of these basins effectively became an enormous inland sea, and over enormous stretches of time, that trapped water simply evaporated away entirely, leaving behind massive deposits of pure salt where an ocean used to sit. Later, sediment slowly buried those ancient salt beds under new layers of rock. Eventually, renewed tectonic activity reopened a connection to the wider ocean, and seawater flowed back in, filling these basins once more. What that leaves behind today is a layered structure on the ocean floor, a cap of ordinary sedimentary rock sitting directly on top of colossal buried slabs of ancient salt. The final ingredient needed to actually activate a brine pool is ongoing tectonic activity, which keeps cracking and fracturing the seafloor in these regions. Seawater seeps down through those fractures until it reaches the buried salt layer, dissolving it and turning into an intensely concentrated brine. Warmed by heat radiating up from deep within the Earth's crust, and that dense, salty, superheated water rises back toward the surface, but because it remains so much denser than the ocean water around it, it settles right back down onto the seafloor instead of dispersing, continuously replenishing the lake from below. That's the entire mechanism, a self-sustaining, naturally occurring reservoir of extraordinarily salty water, constantly topped up with minerals and heat from deep inside the planet. In effect, these brine pools function like alien worlds sitting right here on Earth's own ocean floor, their chemistry, temperature, and pressure resembling conditions you'd expect to find on a distant exoplanet rather than anywhere on our own. To be absolutely clear on one point before going further, no, a person could never actually swim in a lake like this. Setting aside the chemistry entirely, the crushing pressure at a depth of over a mile would destroy a human body long before it ever reached the lake's surface. But it's worth running a thought experiment anyway, imagining what it would actually feel like if one of these lakes somehow existed on land instead of the ocean floor. The very first thing you'd notice stepping into it would be the density of the water itself, far thicker than anything you've ever experienced, closer to viscous syrup than liquid, resisting your movement at every step. You genuinely couldn't drown in it. The density is so extreme that it would physically push your body back up toward the surface, almost like standing on a liquid mirror. Next would come the smell, and by most accounts, it's among the worst odors imaginable, caused by hydrogen sulfide gas continuously released from the brine, producing an overpowering, concentrated stench of rotten eggs thick enough to hang in the air around the entire lake. As bad as that smell is, though, It's nothing compared to what happens the moment your skin actually makes contact with the water itself. The extreme salt concentration would trigger severe irritation almost immediately, quickly escalating into chemical burns, while airborne vapors carrying heavy metals would begin attacking your lungs, liver, kidneys, and nervous system simultaneously. Stepping into a brine pool wouldn't just be uncomfortable, it would be the equivalent of walking directly into a fully lethal chemical trap. That brings up an obvious and darker question. What actually happens to marine life that accidentally wanders into one of these pools? The answer is about as blunt as you'd expect. They die, essentially, every time. Sam Purkis, a professor and head of the Department of Marine Geosciences who led the expedition that first documented the Red Sea Lake, has noted that no living creature, whether fish, shrimp, worm, or mollusk, is able to survive once it crosses into that water. The moment a fish enters a brine pool, it experiences immediate osmotic shock, as the extreme salt concentration outside its body begins violently pulling water out of its cells. On top of that, these lakes contain essentially no dissolved oxygen at all, meaning there's nothing left for a gilled creature to actually breathe. And in its place, heavy metals and toxic compounds flood directly into the bloodstream through the gills, burning tissue and causing death within moments. Over time, the floor of a brine pool tends to accumulate the remains of creatures unlucky enough to have crossed that boundary. And some research expeditions have documented entire graveyards of dead organisms, ringing the edges of these formations, a visible, physical record of exactly how sharp the line is between the surrounding sea and the deadly water sitting just beyond it. Sometimes, though, hunger overrides that instinct for self-preservation entirely. In footage captured at a brine pool in the Gulf of Mexico, researchers recorded an eel repeatedly diving into the lake in short bursts, desperately searching for something edible, each dive functioning as a genuine gamble against death, since even a brief delay resurfacing can mean absorbing a lethal dose of toxins. In one particular dive captured on camera, the eel simply never made it back out, coiling into convulsions from the toxic exposure before going still entirely. A stark, real-time demonstration of just how unforgiving these environments actually are. Given everything described so far, you'd reasonably assume nothing could possibly live inside a brine pool itself. And yet, that assumption turns out to be wrong. Scientists have discovered thriving populations of extremophiles, primarily bacteria and archaea, that have adapted specifically to conditions that would kill essentially any other organism on the planet. Rather than relying on oxygen and sunlight the way most life on Earth does, these organisms derive their energy directly from chemical reactions, oxidizing sulfur or methane compounds instead, an entirely different biological strategy known as chemosynthesis. Their unique cellular structure allows them to survive and even flourish directly inside the toxic, oxygen-starved brine itself, in conditions otherwise fundamentally incompatible with life as we understand it. As microscopic as they are, these extremophiles collectively build entire miniature ecosystems, complex food webs where every organism depends on the one before it. Thanks to their presence, other larger creatures are able to survive right at the boundary of these lakes as well, including small crustaceans and polychaete worms that feed along the shoreline of the brine pool, relying on the biological resources the extremophiles generate. These organisms have genuinely forced scientists to rethink long-held assumptions about what habitability even means. Purkis has suggested that these underwater lakes may hold real clues to how life first emerged on Earth billions of years ago, since the prevailing scientific theory holds that the earliest living organisms arose in oxygen-free ocean depths under conditions strikingly similar to what exists inside a modern brine pool today. If that's accurate, these formations may essentially function as living laboratories, recreating right now the same fundamental chemical conditions that gave rise to life on this planet in the first place. There's an even bigger implication buried in all of this, because these salty, oxygen-starved lakes are also helping scientists think seriously about whether life could exist elsewhere in our own solar system, not on some distant exoplanet light years away, but far closer to home. In 2018, a team of researchers analyzing radar data collected beneath the southern polar ice cap of Mars made a genuinely startling discovery. Roughly a mile beneath the Martian surface, they detected clear signs of hypersaline subsurface lakes. The finding came from Europe's Mars Express orbiter, using an instrument called MARSIS, which picked up radar reflections consistent with liquid water, including one large lake roughly 12 miles across and 3 smaller ones each around 6 miles wide. Scientists believe the extreme salinity of that Martian water is precisely what keeps it liquid at all, preventing it from freezing solid despite the brutally cold temperatures at the Martian poles. Much like their counterparts here on Earth, these Martian lakes are almost certainly devoid of oxygen, drawing an unmistakable parallel to the brine pools sitting in our own oceans, and raising an obvious question. If life managed to establish itself in these kinds of conditions on Earth, why couldn't something similar have happened or still be happening in the salty depths beneath the Martian ice? That same question extends even further outward to Europa, one of Jupiter's moons, and, according to many astrobiologists, one of the single most promising places in the entire solar system to search for life beyond Earth. On the surface, Europa looks like a frozen, lifeless world, its icy crust locked at temperatures around negative 150 degrees Celsius. But roughly 10 to 15 miles beneath that ice sits something remarkable. A global ocean of liquid water that may run as deep as 60 miles, holding an estimated total volume roughly twice that of every ocean on Earth combined. That subsurface ocean is believed to be salty and remarkably ancient, roughly 4 billion years old, meaning it likely formed not long after the solar system itself first came together. Given that immense time span and enormous volume of water, the possibility of life having emerged there, potentially resembling the extremophiles found in Earth's own brine pools, no longer seems far-fetched at all. That possibility is significant enough that NASA has already committed to investigating it directly. The Europa Clipper spacecraft is currently en route to the Jovian system and is expected to enter orbit around Europa in 2030, tasked specifically with gathering the data needed to help answer one central question: whether life could exist beneath that moon's icy shell. Water keeps coming up as the essential ingredient scientists look for when searching for life anywhere in the universe, and that's precisely why NASA, an agency built around exploring space, has increasingly turned its attention toward Earth's own deep ocean instead. It might sound like an odd pivot for a space agency, but the parallels are hard to ignore once you actually think them through. The deep ocean shares several defining traits with outer space: crushing pressure, total darkness, and extreme cold, conditions once assumed to be almost entirely hostile to life. What surprised researchers was discovering that the deep ocean is, in fact, teeming with life, thriving in conditions once considered biologically impossible, from bioluminescent creatures glowing in total darkness to organisms that have adapted to pressure that would instantly crush most other living things. NASA's interest lies in finding comparable forms of life that might exist elsewhere, on icy moons like Saturn's Titan, which is also believed to hide a subsurface ocean capable of supporting life. NASA's connection to deep-sea research actually dates all the way back to the 1960s, right in the middle of the space race, when scientists began recognizing that studying the ocean could teach valuable lessons about surviving in extreme isolated environments, lessons directly applicable to the vacuum of space. Around that same period, the U.S. Navy launched its own ambitious underwater program called SEALAB, built on a simple but powerful premise. If humans could learn to survive extended stays deep in the ocean, that knowledge could translate directly into surviving extended stays in space. SEALAB 2, launched in 1965, reached a depth of 205 feet, with aquanauts living inside an underwater habitat for weeks at a time, conducting experiments and testing new equipment in a genuinely groundbreaking demonstration that humans could adapt to prolonged life in extreme environments. Not every mission ended successfully, though. SEALAB 3, in 1969, ended in tragedy when a fatal accident claimed the life of an aquanaut, and the broader SEALAB program was eventually shut down. Even so, the lessons learned from those missions carried forward, directly shaping the design of both future underwater habitats and later space missions. Today, NASA continues using the ocean as an active training ground for astronauts. The Aquarius Reef Base, an underwater laboratory sitting roughly 62 feet below the surface off the coast of Florida, is home to NASA's NEMO missions, short for NASA Extreme Environment Mission Operations. Inside Aquarius, astronauts train for the disorienting realities of space travel, practicing spacewalks and equipment repairs, while contending with many of the same physical and psychological challenges they'll eventually face aboard the International Space Station or on a future mission to Mars. Life inside the habitat is deliberately cramped and utilitarian, every square inch engineered to mimic the constraints of actual space travel, right down to the reliance on carefully managed life support systems for even the most basic daily tasks. NASA's broader interest, though, extends well beyond training exercises. The agency is genuinely interested in exploring the deepest and most extreme regions of Earth's oceans directly in search of life, on the theory that if life can be found thriving there, similar life could plausibly exist on other worlds with subsurface oceans of their own. That kind of exploration is genuinely difficult, though, given the immense pressure and corrosive salinity involved, and while NASA has helped develop advanced deep sea probes over the years, not every attempt has succeeded. One of the most extreme of these deep ocean environments is the Mariana Trench, located in the western Pacific, and stretching more than 1,500 miles long and up to 43 miles wide, an area roughly 120 times larger than the Grand Canyon. What truly sets it apart, though, isn't its size, but its depth. The lowest point within the trench, known as Challenger Deep, sits nearly 7 miles beneath the ocean's surface, where atmospheric pressure reaches a bone-crushing 15,000 pounds per square inch. Reaching that depth requires an extraordinarily specialized vessel, and to date, only a small handful of people have ever actually done it. Back in 1960, U.S. Navy Lieutenant Don Walsh and Swiss engineer Jacques Picard climbed into a submersible called the Trieste, a bathyscaphe specifically engineered to withstand the crushing pressure of the deep ocean. Its massive float, filled with gasoline for buoyancy, and an 8-foot diameter pressure sphere, built from 2 hemispheres of steel over 3.5 inches thick, welded together and just large enough to hold the 2 men. As they descended, sunlight faded entirely, the temperature dropped toward freezing, and the surrounding pressure climbed past 1,000 atmospheres, enough force to crush most conventional submarines outright. The Trieste held. After nearly 5 hours, Walsh and Picard became the first humans in history to reach the bottom of Challenger Deep, and for decades afterward, they remained the only ones who ever had. What they found down there was genuinely surprising. Life, including a flatfish and other organisms, thriving even at the absolute deepest point in Earth's entire ocean. It wasn't until 2012, more than 50 years later, that another explorer took up the same challenge, filmmaker James Cameron, piloting a sleek, purpose-built vertical submersible called the Deep Sea Challenger. On March 26, 2012, Cameron completed a solo dive to the bottom of Challenger Deep, reaching a depth of 35,787 feet, and becoming just the 3rd person in history to make the journey, documenting strange, previously unseen creatures along the way, including something researchers came to call the squid worm. NASA's Jet Propulsion Laboratory has also lent its expertise to deep-sea robotics, contributing technology developed for planetary rovers and icy moon probes to projects like Orpheus, an autonomous underwater vehicle built in partnership with the Woods Hole Oceanographic Institution specifically to explore the ocean's most extreme trenches. An earlier vehicle in that same lineage, Nereus, was lost in 2014 during a mission to the Kermadec Trench, likely destroyed by a catastrophic implosion under the immense pressure at nearly 32,800 feet. Beyond the brine pools and the deepest trenches, the ocean has continued to reveal creatures so strange they seem to belong on another planet entirely. There's the gulper eel, a genuinely alien-looking animal, with a mouth disproportionately larger than the rest of its body, hinged wide enough to swallow prey whole and capable of inflating like a balloon when threatened to appear larger to predators. There's the so-called headless chicken monster, which, despite its unsettling appearance, is actually a species of swimming sea cucumber, its deep red coloring coming not from any outer skin at all, but from its fully transparent body revealing the internal organs underneath, typically found at depths between roughly 9,800 and 13,000 feet. There's the frilled shark, an ancient predator with a lineage stretching back an estimated 80 million years, old enough to have shared the ocean with dinosaurs, distinguished by 300 backward-facing needle-like teeth arranged in rows, specifically designed to prevent anything it catches from ever escaping. There's the mantis shrimp, whose fossil record stretches back some 400 million years, and which possesses the most advanced eyesight known in the entire animal kingdom, capable of detecting far more wavelengths of light than the human eye, and capable of throwing a strike so fast and powerful it can crack aquarium glass, generating a cavitation bubble hot enough to briefly reach temperatures comparable to the surface of the sun. There's the vampire squid, whose name is almost entirely misleading since it isn't a true squid and feeds only on falling organic debris rather than blood, distinguished by a dark, cloak-like webbing connecting its 8 arms in a fossil lineage stretching back at least 300 million years. There's the Japanese spider crab, holding the record for the longest leg span of any arthropod on Earth at up to 12.5 feet claw to claw, despite a body only about 15 inches wide. There's the horseshoe crab, which has survived more than 445 million years, and at least 4 of Earth's mass extinction events, including the very impact that wiped out the dinosaurs, its distinctive copper-based blue blood capable of coagulating around invading bacteria. There's the chambered nautilus, with a fossil record stretching back an astonishing 500 million years, predating the dinosaurs by roughly 300 million years. Its spiral shell divided into sequential chambers as the animal continues to grow throughout its unusually long, roughly 20-year lifespan for a cephalopod. There's the yeti crab, covered in silky, hair-like strands that it uses to farm chemosynthetic bacteria near hydrothermal vents, essentially cultivating its own food source in one of the most hostile environments on the planet. There's the box crab, known for its bizarre mating ritual in which the male carries and even buries the female to protect her until she molts. There's the goblin shark, with its unmistakable elongated snout and jaws that can shoot forward to snatch prey, part of a shark lineage estimated to be more than 125 million years old. There's the giant oarfish, the longest bony fish in the world, with some individuals stretching between 33 and 56 feet, tied in Japanese folklore to omens of earthquakes and tsunamis, though no scientific evidence has ever confirmed any real connection between the two. There's the deep water stingray, distinguished by 6 pairs of gill slits rather than the usual 5 in a fossil lineage stretching back roughly 420 million years. There's the sea spider, not a true arachnid at all, but a member of a separate class entirely, with a fossil record dating back some 430 million years, and a body so reduced that its internal organs actually extend out into its unusually long legs. And there's the big-fin squid, so rare that only a handful of confirmed sightings exist worldwide. First documented in Australian waters only in 2020, with a tiny 6 to 7 inch body trailing arms and tentacles that can stretch up to 20 times its own length. Taken together, these discoveries, from lethal underwater lakes hiding on the seafloor to ancient creatures that have outlasted dinosaurs by hundreds of millions of years, paint a picture of an ocean that remains almost entirely unexplored. Despite everything modern technology has allowed scientists to uncover, an estimated 95% of Earth's oceans remain completely unmapped and unexamined, an enormous, largely invisible frontier sitting right here on our own planet. And that gap in knowledge carries implications well beyond Earth itself. If life can establish itself in conditions as extreme and lethal as a hypersaline, oxygen-free brine pool sitting a mile beneath the ocean's surface, it becomes considerably harder to rule out the possibility of life existing in similarly extreme conditions elsewhere in the solar system, whether beneath the ice of Mars's polar caps or inside the vast, ancient ocean hidden under Europa's frozen crust. The deep sea and deep space, it turns out, may not be as different as they first appear. Both remain almost entirely unexplored. Both are defined by extremes that once seemed fundamentally incompatible with life. And both keep revealing that life has a remarkable, almost stubborn habit of finding a way regardless. Every dive into Earth's own deep ocean is, in a very real sense, a rehearsal for the exploration still waiting for us far beyond it.